Good afternoon, students. Let us start the class. In yesterday's class, we had seen the different derivations for different types of feedback topologies. We will continue with the same concept today, and today we will see some of the practical feedback circuits, because till now we have been discussing only the block level circuits. We will see some examples for such feedback circuits. So before that, there is a small derivation again about how gain becomes stable with the feedback. So you can see on the screen now, AF is the gain with feedback, A is the gain without feedback. So we already know that AF is equal to A by 1 plus A beta, where beta is the fraction, that is a small percentage of the output taken back to the input. Now let us take beta as constant, because we want to characterize this A and AF in terms of beta. So taking beta as constant and by differentiating this particular equation, we will get differential of AF equals differential of A divided by 1 plus A beta whole squared, because you already know differential of 1 over x is 1 over x squared. So that way DAF is equal to DA divided by 1 plus A beta whole squared, or DAF divided by AF is DA divided by 1 plus A beta whole squared into 1 plus A beta divided by A. So we are differentiating with respect to AF here. So it's dA by 1 plus A beta whole squared into 1 plus A beta divided by A, that is 1 by 1 plus A beta into dA by A. Now when A beta is much larger than 1, DAF by AF is going to be 1 by A beta into dA by A. We can ignore this particular term 1 with respect to 1 plus A beta. Now you can see that the differential of the feedback gain is 1 by A beta times the differential of the open loop gain. That means now the gain is reduced by A beta times when compared to the open loop gain. Now this is how we can say the gain is becoming stable, in the sense with respect to the open loop gain also, the closed loop gain is reduced by a terminology of A beta. Let us see an example for this particular expression. An amplifier has a gain of 800, that is capital A is given as 800 and feedback of 0.15, that means beta is 0.15. If it has a gain change of 10% due to temperature, calculate the change in gain in the feedback amplifier. Now given A is 800 and beta is 0.15 and there is a gain change of 10% due to temperature, that means this capital A is going to change by 10%. Let us find out the change in gain with feedback. So we have DAF by AF is 1 by A beta into dA by A, right? Now dA by A is given as 10%, that is 0.1, and 1 by A beta, A is 800, beta is 0.15. So 1 by A beta into 0.1 is 0.083%. Now we can observe that the open loop gain changed by 10%. You can see here, open loop gain changed by 10%, whereas the closed loop gain changed only by 0.083%, which means with the negative feedback, the gain is becoming more stabilized. You can see this. Even when the open loop gain changes by 10%, the closed loop gain did not change even 1%. It is around 0.083%. That means the gain with feedback is more stabilized with negative feedback. Now let us see some practical feedback circuits. The first example is voltage series feedback. Now you can see, you will not see the amplifier circuit fully here. The FET itself is working like an amplifier here now with only the drain resistance. As we already know, for the gate there is no need of a resistance. We have been using resistance only for biasing the FET. Now you can see this complete FET circuit is an amplifier circuit along with the load resistance, and at the output we have one voltage divider network R1 and R2. By using this R1 and R2, we are going to fix up the factor beta. You already know that the small percentage of output is fed back to input. That way, if R2 is smaller, is R1 is larger, then whatever is the voltage across R2, that is going back to input. But you can see that always there is a voltage source at the input. Now this is connected in series with that. So that way, now voltage is taken across R2 and it is given in series with the input voltage. Now, how is it negative feedback? Negative feedback. How is it negative feedback? Let us see. Now, when this input signal is rising, here the output signal is going to fall, right? When the input signal is rising, there is output signal is going to fall. Now, small percentage of that output signal itself is taken here, right? Across R2. That means now the feedback signal is out of phase with the input signal. That means now this is basically a negative feedback. That means the input signal's amplitude is going to be reduced by the application of the feedback signal. So this way it is a negative feedback circuit. So let us see how to analyze this circuit now. We have A equals V0 by Vi. Now we already know that gain is given by Gm into Rd in the earlier cases. Now we have RL in parallel. Along with that, we have R1 plus R2 also in parallel. Earlier we had derived this expression for the voltage gain without considering the load resistance. Now here we have load resistance and here we have the voltage divider network which is taken as a feedback network. So we have Rd in parallel with RL in parallel with R1 plus R2 into Gm. Now what is beta? Beta is Vf by V0. That is nothing but R2 divided by R1 plus R2, because we are taking the feedback voltage across R2, whereas the net voltage or the complete output voltage is across R1 and R2. So fraction beta is R2 divided by R1 plus R2. So now we have this formula already, ready formula, AF equals A by 1 plus A beta, which we had derived earlier. Now let us substitute for A as well as beta. For A, Gm multiplied with Rd parallel with R1 plus R2, and then 1 plus A into beta. Beta is nothing but R2 divided by R1 plus R2. You can see that it is multiplied here. Now this is the expression given for the gain with feedback. When A beta is much larger than 1, usually that will be the case. When A beta is much larger than 1, then AF can be R1 plus R2 divided by R2. How? You can see this R1 plus R2 which is at the bottom. Let me choose a different color. Now this R1 plus R2 which is at the numerator, then denominator, and it is in the denominator. So it is going up here. Okay. R1 plus R2 is going up here. R2 remains here. Now when A beta is much larger than 1, this unity, that is 1, this 1 can be ignored. Let me choose a different color. Now this 1 can be ignored. When this 1 is ignored, this term gets cancelled with this term. And that is how we get R1 plus R2 divided by R2. provided when A beta is much greater than 1. Otherwise, we cannot ignore those terminologies. So now the gain with feedback is R1 plus R2 divided by R2, means the gain with feedback or the closed loop gain is completely independent of the open loop gain. You can see here, AF is dependent only on the values of R1 and R2. It is not dependent on the gain of the amplifier circuit also. That way AF is equal to R1 plus R2 divided by R2, provided A beta is much larger than 1. This is one example of the voltage series feedback, and the circuit directly is showing or circuit directly indicating that the feedback voltage is in series with input voltage, and as the feedback voltage is antiphase with input voltage, now this is a negative feedback only. Now there is another example for this voltage series feedback, that is emitter follower. In module 1, we had already seen the circuit of emitter follower. But how an emitter follower is going to work like a voltage series feedback? You may think that in that emitter follower there is no feedback at all. No, we were only giving input and we were getting output, and that particular circuit's gain was unity as such. We had derived it already. So you may think that for this voltage series feedback, emitter follower may not be having any feedback. But let us examine that closely now. We will see that the circuit is going to have a feedback. Let us see that now. We are seeing the emitter follower circuit. Now you can see we are taking output at the emitter resistor. That means as we are taking output at the emitter resistor and as we are applying input between base and ground, now when voltage across RE increases, that is going to reverse bias the base to emitter junction. When it is going to reverse bias the base to emitter junction, even though we have not directly taken the output's fraction back to input, without any such connection, already output itself is working as a feedback signal to the base to emitter junction. You can see that the base to emitter junction is reverse biased with respect to output. So if output increases beyond a certain value, then the base to emitter junction is going to be reverse biased. And when the base to emitter junction is going to be reverse biased, the conduction of the transistor itself is going to be affected. That way, this is a negative feedback. And it is again a voltage series feedback. How is it a voltage series feedback? Let us see that. This is a voltage series feedback circuit with Vi equals Vs and Vf equals V0. Input voltage to the complete amplifier is Vs itself, and output voltage itself is the feedback signal here, because let me write by annotating. Let us say we have an input signal like this. Now the same input signal is going to appear as output here now, right? Now there is no antiphase here as far as input and output are concerned, because emitter follower is basically a common collector amplifier. It is not going to give any 180-degree phase shift. But when you compare this V0 with the voltage at Vs, whenever this V0 is rising, what is happening? Whenever V0 is rising, emitter is rising to a larger potential, and when emitter is rising to a larger potential, actually the base to emitter junction will be reverse biased. So as such, between Vs and V0 there is no phase shift. Still, due to the connection itself, output voltage is working like a feedback signal, and the source voltage itself is the input signal. That is why this is like a voltage series feedback circuit, because Vs and V0 are in series actually. So that way, if we continue the analysis now, gain A is V0 by Vi, that is HFE into IB into RE divided by Vi. What is V0 now? There is a emitter current across this RE, AC current, that is HFE into IB. HFE is nothing but beta with respect to transistor. It is not the fraction which we used in this module. So, but I am purposefully using the symbol HFE itself. HFE into IB into RE or IE into RE is output voltage. And we have VI here. Now, what is that IB by VI? VI by IB is nothing but HIE, the input impedance with respect to the hybrid parameters. VI by IB, input voltage divided by input current itself is HIE. So, IB by VI is going to come at the denominator. That means the gain of this particular amplifier is HF into capital RE divided by HIE. Even though we had seen earlier that the gain of emitter follower is almost equivalent to unity that we had derived earlier. We are going to have it now also here, but we are discussing emitter follower with a different angle now. We are discussing as if it is a negative feedback circuit. Now, beta is Vf by V0. Vf is V0 only, right? Actually, output voltage itself is the feedback voltage here. So, Vf by V0 is basically unity in our case, in this particular case. Now, we have the expression for A, we have the expression for beta. Let us try to find out the gain with feedback. AF is equal to A by 1 plus A beta. We will arrive at AF equals A by 1 plus A only, right? We will see that. Now, AF is equal to A by 1 plus A into beta, where A is HF into RE divided by HIE, and then 1 plus A into beta. Beta is 1 only. So, it is 1 plus HF into RE divided by HIE. Now, this is nothing but HF into RE divided by HIE plus HF into RE. When you simplify this expression using HIE, we will get HIE common here with this HFE RE term. Now, 1 gets multiplied by HIE. So, we have HF into RE divided by HIE plus HF into RE. Now, if HF into RE is much greater than HIE, in general, HF is always larger only, right? And HF into RE, if it is much larger than HIE, then what happens? When this particular term is much larger than this particular term HIE, AF will be approximately equal to unity only. This we had proved in the AC analysis in the first module when we discussed common collector amplifier or emitter follower. Now, the same thing is applicable here as well. Actually, it cannot change that way, right? Only thing is we try to analyze the emitter follower circuit with an angle of negative feedback. So, this has been proved earlier as well that AV equals 1. Here the same circuit is analyzed in terms of voltage feedback. That's all. So, we have seen 2 examples of voltage series feedback and that negative feedback. Let us see an example of voltage shunt feedback now. Now, again, this is an FET amplifier and we can see a source voltage here and you have a source resistance. Then this FET is having a drain resistance and a source resistance. The source resistance is purposefully mentioned as R1 because we have an input signal source resistance that is mentioned as RS. That is why the device's source resistance is mentioned as R1. And we already have a bypass capacitor at the source of the device. Now, you can see this feedback resistance RF. Now, this voltage is fed back in shunt. How do we say that? See, here there is this, let us say this is now plus and minus. Source voltage is there. Now, there will be output voltage across this. Now, this is a common source amplifier. So, when this is plus and minus, we can consider this as minus and plus. Output as minus and plus, because when input signal is rising, output signal will be falling. That we already know in the case of a common source amplifier. So now portion of the signal itself is fed back to the input by means of this RF. Let us say we have this input signal here and the output signal is in a phase shifted version, 180-degree phase shifted version of the output. Now the same signal, portion of it is coming through this RF to the input. That means what? Now this is minus and plus, because output is minus and plus. That means we will have a small portion here at gate. Now you can see it is a voltage shunt feedback only. Why? This input source and this feedback voltage are in parallel. In between them there is this RS. But while we were analyzing the circuit mathematically, we had purposefully connected a current source there. Why? Because we had not considered the input source's resistance in series. And I had mentioned you there that if there are two voltage sources in parallel, it will be very difficult to analyze them, because which one is going to dominate? That is a difficult task there. That is why while analyzing we had purposefully used current sources there. But here this is a practical example. In the practical example there is no current source, and this has to be considered. This source resistance from the input side has to be considered. Why? If this is not there, what will happen? These two will become totally parallel with each other, and which one is dominant? It is very difficult to analyze that. Which one is dominant? Difficult to analyze. And we have to go for instantaneous analysis of each waveforms. So you can see now that this is a voltage shunt feedback circuit. When we connect a feedback resistance from the output back to the gate, it is working like a voltage shunt feedback. Now for the sake of our analysis, let us replace this particular circuit slightly in a different fashion. Because if you have to analyze, then it is better to have a current source only, as I told you earlier. So now with the Vs and Rs together, we will replace it as Is here. Is is nothing but Vs by Rs there. Now we have this If, the feedback current, and we have this Rf. From the drain to the gate, we have this Rf. Rs is not indicated here. Why? Let me annotate. This whole of Rs and Vs. Whole of this Rs and Vs is replaced with this particular Is. Is is nothing but Vs by Rs. And then between drain and gate there is this Rf. Okay, so that is connected. Now there is this RD. RD is AC ground anyhow, right? VDD is AC ground. RD is other end is AC ground. So that RD is connected directly to ground. And R1 need not be connected here. It can be directly shorted. Why? Because of this bypass capacitance, R1 is shorted to ground. So that way we have written the AC equivalent of the circuit which you are seeing at the left side. So now let us proceed with our analysis for this particular circuit. This is an example of a voltage shunt feedback. So now A is V0 by Is, as we have replaced Vs and Rs with Is. A is V0 by Is. You might recall that voltage shunt feedback was also called as current to voltage converter, right? Input was current, output was voltage. It is the same thing here now. Input is current, output is voltage. So it is a current to voltage converter. Okay. Or it is a transconductance amplifier or trans resistance. It is V0 by Is. So it's a trans resistance amplifier. So open loop gain is V0 by Is. We can write it as V0 by Vs into Vs by Is. Okay. Now V0 by Vs is nothing but Gm into Rd. This we have already seen in module 2 when we discuss the AC analysis of JFET amplifiers. So V0 by Vs, let me annotate, V0 by Vs is nothing but Gm into Rd, and Vs by Is is nothing but this Rs. Vs by Is is nothing but Rs. That way, open loop gain is Gm into Rd into Rs. Now let us see the closed loop gain. What is beta here? Beta is If by V0. It's the fraction of the output coming back to input, but input is current here now. So beta is If by V0. That If by V0 can be easily approximated to 1 over Rf, because you can see here in the equivalent circuit that one side there is V0, this side there is If. So If by V0 is nothing but 1 over Rf. Current is entering into Rf, the other end of Rf is connected to voltage. So we should write that Rf is equal to V0 by If, or 1 over Rf is If by V0. That is the feedback factor. So beta is If by V0. Let us substitute these terms in our regular expression A by 1 plus A beta. So now AF is V0 by Is, right? The gain with feedback is V0 by Is, as we have seen in this particular diagram. Output is V0, input is Is. So AF is V0 by Is, that is A by 1 plus A beta, that is Gm into Rd into Rs divided by 1 plus Gm into Rd into Rs divided by Rf, substituting 1 over Rf. Now you may get confused here. I have written A also as V0 by Is and AF also as V0 by Is. Okay. In fact, we are giving a feedback through Rf, right? Through the resistance. Now you can say how the equation for open loop gain as well as closed loop gain can be same. That may be your question. Okay. I think I have made a mistake here. Yes, I have made a mistake here. AF is V0 by Vs. It is not V0 by Is. We should take it this way. Let me correct it in my notes also later on. It is AF is equal to V0 by Vs. So when AF is, that is correct now. Because output is V0 here, input is Vs here. So V0 by Vs is nothing but A by 1 plus A beta. That is substitute for A, substitute for beta. We will get AF is equal to this particular expression, Gm into Rd into Rs into Rf divided by Rf plus Gm into Rd into Rs. Now this is the expression for the gain with feedback. Now actually this AF, wait a minute, I am also getting confused, I am confusing you also. As we are discussing a trans resistance amplifier, now the gain A is basically that Rm which I mentioned earlier, right? I had written one small r and small m with the suffix there. I had mentioned that it is a mutual resistance or trans resistance. Now this AF is basically a trans resistance. That is why this expression is correct. V0 by Is is correct. We have obtained an expression for trans resistance or the gain in that terminology. Here we have the voltage gain with feedback. AF is a gain with feedback, not for voltage, it is for trans resistance. Okay. I'm sorry that I confused you in between, because even I did not see the expression which was below. I'm just moving this PDF page by page, right? So I clearly don't remember what equation I have written at the bottom unless I see that and I recall. Of course, that way teaching is sometimes challenging. We have to have our speech and our hands and our brain all under synchronization. Anyway, So AF is equal to GM into RD into RS into RF divided by RF plus GM into RD into RS. Or now the voltage gain with feedback is V naught by Vs. That is correct. That is where I tried to correct it there. My notes is now correct. So AVS is equal to V naught by Vs is equal to, we can write it as V naught by Is into Is by Vs. Now for V naught by Is, we already have the expression. And for Is by Vs, it is nothing but 1 over Rs. Let me admit the student. So this Is by Rs, Is by Vs, sorry, Is by Vs is nothing but, here it is a Rs. I by V is 1 over R. That is there. And V naught by Is, we already have this formula. Okay. That way, here we had this Rs and here we had that one more Rs. This Rs gets cancelled with that other Rs. In fact, we have not substituted Is by Vs as Rs here. Let me stop annotating and let me write annotation in a different way. This Is by Vs is getting cancelled here, because at the numerator you have this Rs. When we multiply by Is by Vs, that is 1 over Rs, that is getting cancelled here. So naturally you have Gm into Rd into Rf divided by Rf plus Gm into Rd into Rs. That is the expression for gain of voltage with feedback. So this was an example of a voltage shunt feedback. Now there is a small problem or exercise for the given voltage shunt feedback. Calculate AVF, voltage gain with feedback. Given Gm is equal to 5 millisiemens, Rd is equal to 5.1 kilo ohms, Rf or the feedback resistance is equal to 20 kilo ohms, and Rs or the source resistance is equal to 20 ohms. Source resistance means resistance at the input source. Now capital A is Gm into Rd into Rf, right? 5 milliseconds into 5.1 kilo ohms into 20 kilo ohms. I should write it as 20k here, right? I have left out the k here. No, now let me correct it. No, it is Rs, not Rf. Gm into Rd into Rs, right? Yeah. Why should I confuse you again and again? Capital A is Gm into Rd into Rs. That way answer is correct. So it is Gm into Rd into Rs, that is 510. Now AVF is what? AVF is Gm into Rd into Rf divided by Rf plus Gm into Rd into Rs. So that is 510 into 20k, that Rf is there, divided by 20k plus 510 Rf plus Gm into Rd into Rs. So we get around the gain as 497.32. That is the gain with voltage shunt feedback. Now we are coming to the last example, that is the current series feedback. In a common emitter amplifier, if the emitter resistance is unbypassed, then it results in a current series feedback. Now this is a common emitter amplifier, and in this common emitter amplifier, you will see that the bypass capacitance is not there. Across Re, there is no bypass capacitance. Now when there is no bypass capacitance, this is becoming like a current series feedback. How? Let us see. Here IE as part of the output current results in Vf. There is a emitter current. We have seen in emitter follower circuit there that the output voltage itself was working like a feedback, but that was a voltage feedback. Here, as there is no bypass capacitance, we have this emitter current now, but we are taking output at the collector itself. Now we have the emitter current here. Now the emitter current is going to vary because there is no bypass capacitance. Whenever we have an input signal, let me annotate this. Let us say we have an input signal in this way. Now we have an output signal in this way, but we will have an emitter signal in this way. the signal at the emitter will be in phase with the input, because there is no phase shift at the emitter. There is only a phase shift at the collector. So now, as we do not have the capacitance, now this signal will remain AC here. Now when the signal remains as AC here, the change in the emitter current is working as a feedback. As I had discussed in the emitter follower, the same thing holds good here also. There is a reverse bias between base to emitter junction. So IE as part of the output current results in VF such that V0 is reduced now. Now as there is no bypass capacitance, output voltage gets reduced and this results in the negative feedback. Now you can say, how is it current series feedback? It is current series feedback because you have this input current IB, then you have this IE going. Part of IE is itself working like feedback. That way, two currents are in series. You can see that both IB and IE are in series. That way, it is a negative feedback because the base to emitter junction is reverse biased. That way, this circuit is a current series feedback circuit. Now the circuit is analyzed without feedback and with feedback together. Let us see how to do that. Let us first see without any feedback and later we will see with feedback. Now, as I am moving my PDF page, you will have to remember that diagram now. That is basically a common emitter amplifier without the bypass capacitance. You will have to recall that diagram whenever we discuss this equation. Now without feedback, the open loop gain A is IE by VI. IE and IC both are same, right? So it is basically a voltage to current converter now, or we can call it as a trans conductance amplifier now. We are taking output as current here because we are taking it as a current series feedback. Please remember, we are analyzing this circuit with respect to feedback. Don't get confused with the way in which we analyzed it in the first module. In the first module, we actually found out the AC gain by performing AC analysis. That is also quite accurate. But here we are trying to analyze this circuit without feedback. Of course, in the first module when we discussed the same circuit, we had that bypass capacitance there. Now we don't have this bypass capacitance. So A is equal to IE by VI. What is IE? IB into HFE. And what is VI? IB into HIE. Right? Input voltage is nothing but input current into the input impedance for the transistor. So that way IB gets cancelled. We have the open loop gain A is equal to HFE by HIE. Now what is beta? Beta is VF by IE. The feedback voltage divided by the current. What is this VF? VF is nothing but IE into RE. So IE gets cancelled and we have the beta as RE itself. The emitter resistance itself is now the feedback factor. How? Basically beta is what? Portion of the output taken back as the input. Input is taken back as the input, that feedback is VF. And that output is IE. So naturally we will get beta equals RE. Now the input impedance Zi is equal to RB in parallel with HIE plus RE. You will have to please visualize, or let me go back. We have this RB and then we have this HIE, then we have this RE, right? So when you go for AC analysis, RB's other end is connected to ground, AC ground. So RB is in parallel with HIE here between base to emitter, plus it is in series with RE. That way we have Zi is equal to RB in parallel with HIE plus RE, and Z0 is nothing but RC. Output impedance is nothing but RC. You can see here with respect to output it is only RC. So when RB is much larger, which is generally the case, base resistance is much larger, and when HIE is also much larger than capital RE, emitter resistance will be slightly lesser when compared to HIE, we can directly say that input impedance is nothing but HIE itself. because HI will be larger, but RB will be much larger. Whenever there are one larger resistance and a smaller resistance in parallel, the value will be nearer to the smaller resistance only. You already know that. So when RB is much larger, RB can be completely ignored. And when the small capital RE is smaller than HIE, even this RE can be ignored. So that way ZI will be HIE. These are some approximations we are making. So now ZI is equal to HIE, Z0 is equal to RC. This is without feedback. Now let us say with feedback, we have this AF. Please remember, now this A is nothing but transconductance. Let me not confuse you further as I confused in the previous case. I have specifically written AF, means it is the open loop, it is the closed loop gain, but the closed loop gain is basically transconductance. Output is IE, input is Vs. We have a ready expression A by 1 plus A beta. Substituting all that for A and for A into beta. Substituting all that, we get this expression AF is equal to HFE divided by HIE plus HFE into RE. So the input impedance is nothing but ZI into 1 plus A beta, and we can substitute. ZI is already HIE. For 1 plus A beta we can substitute. This is now input impedance with feedback, or we can write ZIF is equal to HIE plus HFE into RE, because anyhow this HIE is going to be cancelled out. Now ZOF, output impedance with feedback, is ZO into 1 plus A beta. ZO is nothing but RC. Let us substitute for 1 plus A beta, that is 1 plus HF into RE divided by HIE. So this way we have found out the expressions for the closed loop gain and the input impedance as well as the output impedance with feedback. A small exercise based on the derivations whatever we had. Calculate the voltage gain for the circuit given below. Now this is the circuit given. You can see that there is no bypass capacitance. That means this is a circuit with current series feedback. So all other things are given. RB is given, RC is given, HFE is given, HIE is given, RE is given, and input voltage 10 millivolts is given. And the VDD, VCC plus 16 volts is given. So we have to find out the voltage gain, and let us try to solve this. Answer is AF is equal to 120 by 4000 plus 120 into 510. What is AF? AF is nothing but HFE divided by HIE plus HFE into RE. Substituting that, we get this value. That is, this is a transconductance. We get around 1.84 into 10 power minus 3. Now AVF is V0 by Vs. What is V0? IE into RC and divided by Vs. Now IE divided by Vs into RC. We can substitute for IE divided by Vs. That is AVF. IE divided by Vs is nothing but this 1.84 into 10 power minus 3. So AVF is equal to 1.84 into 10 power minus 3 into 2.2K. That means we are getting around 4.05. You can see the transconductance gain is given by 1.84 into 10 power minus 3, whereas the voltage gain with feedback is only 4 now, 4.05. So this is the outcome of the current series feedback. Now with this I have completed the practical feedback circuit examples. Let me stop the class for now, and in the next class we will start discussing some other interesting topic about phase margin and gain margin. And later on, let us start discussing the next part of this module, that is oscillators. Oscillators are nothing but amplifiers with positive feedback. So I have almost ended the discussion on negative feedback, except that in the next class we will have a brief discussion about what is meant by gain margin and phase margin. Later on we will start discussing the positive feedback circuits. So I am ending the class for today. Take care. and see you in the next class.